This is our continuing series, Elite Engineers, our continuing webinar series. Today we have John Emmenheiser from CH2M, and he's going to talk to us about pushover analysis of a torsionally eccentric cellular abutment. I'm going to now make John our presenter, if you give me a second. There you are. And John, you should now be able to select your screen you want to share. Yes, we can see your slides, so you can go ahead and get started when you're ready.
Okay, thank you. So today we'll go over the pushover analysis for a torsionally eccentric cellular abutment. Some copyright information. Moving into the presentation outline, I'll go through a project overview, go through the superstructure analysis, substructure analysis for the model, a little bit in the elastic analysis and inelastic, and then move into the pushover analysis in the MIDAS Civil 3D program. We'll start with the elastic model, go into the general section designer, which is a sub-tool of the program, and then move into the pushover analysis. Then go through some results, the comparison of those results, and also into the design of the shear and the detailing of the elements in the structure. So an overview of the presentation, the objectives will be to understand the modeling techniques for the inelastic analysis, and that's using the MIDAS General Section Designer as well as the MIDAS Civil 3D Pushover Analysis. Just a few limitations. Won't go into any of the foundation, bearing, and sliding capacity. This is a shallow foundation structure in a high seismic zone and in also a high scour zone. Certainly some questions with that, but that's out of the scope of this presentation. And certainly was designed and everything checked out. I won't be able to explain all the theory behind all the topics. We'll go through a introductory overview of the pushover analysis. Certainly won't be able to go through every checkbox. I won't be using the program live. Strongly recommend as we go through those windows to be familiar certainly with every checkbox and the defaults, but rely on the help menus. The help menus have things well documented and can help in greater detail than I could do in 1 hour today. Also won't go into any of the proprietary algorithms within the calculations in the software. An overview of the project. This is a project that was led by Central Federal Lands, funded by the Federal Lands Access Program. And the location is in Placer County, California, in the northwest edge of Lake Tahoe and Tahoe City. A little bit in the structure selection. The original structure had 3 spans with deep foundations and pretty complicated geometry. Portion of the bridge supported a traffic circle, and that led to the geometry that we can see in the left-hand side, the wide flare and non-parallel girders. So the design was essentially revised to rely on a single main span with shallow foundations and square geometry. And that main span was 119 feet long, simple span decked bulb T-girders with the 14-foot clear opening cellular abutments. And they had the retaining wall toward the embankment and then 4 columns toward the river. And that's what led to the torsional eccentricity in the transverse direction in a seismic event. Just another rendering of the bridge with the elevation view shown there. You can see the shallow foundations with the cutoff walls, superstructure supported on the corbel ledge, columns toward the river, retaining walls away. I'm going to touch just briefly on the superstructure analysis. We did do a model of the superstructure analysis in MIDAS Civil 3D, so I'll bring that up. It was designed with AASHTO LRFD 2012 Caltrans amendments, relied on the deck bulb T-girders with the UDOT typical section. And the girders were set on level bearing seats on the corbel beam, with steel reinforced elastomeric bearing pads. And then a Caltrans request, we had a cast-in-place concrete topping. This isn't necessary for the deck bulb Ts, that was just a special request to the agency, as well as the cast-in-place diaphragms, and then certainly some cast-in-place barriers. So the reason we used the MIDAS Civil 3D design wasn't used for the primary design. We used just a 2D analysis program, a fairly simple straight bridge. We used this to verify the distribution factors. Like I said, the length is 119 feet, single span. It originally was 98 feet, and that was lengthened due to some scour parameters. When we did that, the distribution factors, the conservative AASHTO table factors, had the design a little bit closer to the ultimate value than we would have liked. It was possible to use the conspan grillage analysis that revised the design, although that's a little bit behind the scenes and harder to tell. So we did, just for comparison, we did a Midas grillage analysis. And there's just, one example of the interior moment with the two trucks. AASHTO equations, conspan grillage, and then the Midas grillage, all within the same range, but Midas was slightly less conservative and allowed for working design. Because of the span length and the agency permit truck, the P15 was the design truck that controlled for strength 2. Often strength 1 does control, but in this case we were strength 2. And just quickly on how that was input into the program, in the Structure tab, there's a pre-stressed composite bridge button that opens the window. Going through all the input parameters, pretty robust input wizard that generates a simple span bridge fairly quickly. In my case, I was generating a simple span bridge. There are certainly more options. The abutments that can be seen in the model are added on after the fact. Basically just replaced the bearings that came up with the plate elements for the abutments. So moving into the substructure analysis, again, the design code AASHTO 2012 also used the AASHTO LRFD 2011 guide specification and Caltrans seismic design criteria version 1.7. An overview of the substructure, as we've seen, the spread footings with the toe walls, the columns with the corbel for girder supports, retaining wall for the back wall, and then the solid top slab with the exception of utility voids. Just a side elevation and a front elevation of the structure showing the 4 columns, the side elevation showing the back wall on the left, the columns in the right, and in the transverse direction, that's the eccentricity. For the model, it was originally modeled for primary design in CSI bridge using solid elements, and that allows for stress interaction between the elements in multiple directions. With plates, we're a little bit more limited. With beam elements, it's even more limited. The model in Midas Civil 3D was relying on the plate elements for all structural elements. In the case of the pushover analysis, that does require beam elements, so in that case the columns were replaced with a beam element. The other place relied on the beams was for the corbel design. We idealized the beam to make an approximation of how much of the top slab was serving as a structural element, along with the corbel and the stem down to the corbel to support the girders. And that was input as a beam to get those design forces. For the column properties, in the initial model in Midas Civil 3D, we used the elastic properties. And that's just based on the nominal material properties, basically what's on the plan set. 60 KSI steel, 4.5 KSI concrete. No concrete was assumed to be confined, and we relied on the entire rectangular section. For the element design, the slab elements were analyzed as plates and designed with a 1-foot strip width using reinforced concrete design. There were some stress concentrations around the columns that were taken into account, but for the most part, the reinforcement through the slab was consistent through the slab, and there wasn't significant variation in the spacing. The corbel beam, like I mentioned, the stiffness considerations were given to idealize a beam to represent that L-shaped corbel and also approximate how much of the top slab was serving as a beam element. For the design of the ledge corbel itself, we used the TxDOT design example based on the 2010 AASHTO and certainly checked the 2012 AASHTO for applicability. And that just checks all the independent failure mechanisms, punching shear, the moment about various elements, the pure tension in that stem, the moment about the ledge, interface shear, and so on. For the columns, they were designed to remain elastic during the design event and then detailed for the inelastic region, which would be expected to happen at an event that exceeded the design event. So moving into that with the inelastic analysis, the purpose is to determine to force a plastic moment failure before a shear failure. The image on the left shows a shear failure, which is undesirable, almost would certainly end up in the superstructure collapse. On the right, we have a column plastic hinge, and while that column likely has no shear capacity left, it still is stable and able to support the superstructure above. And the purpose of the analysis is to determine that design value for the shear to ensure that we get that reaction. An overview on the seismic design, the peak ground acceleration was 0.44 Gs, and that was based on the assumption that the period was 0. The reason we can assume that the period is 0 is from the AASHTO LRSD guide spec, section 4.5. And that assumption acknowledges the fact that the period of vibration is fairly difficult to calculate because of the interaction between the structure. And since the bridge is very stiff, we know the fundamental response will be short, so the approximation of 0 is appropriate. And we look at the shear key detail on the bottom right. That shows the bearing pads, the expansion joint material, and the interaction between the girders, all of which will affect the interaction as that shear key begins to yield. The shear key is designed for a quarter of the superstructure weight elastically, and that's based on half of each abutment end reaction. And certainly as it becomes inelastic, the force transfer will be somewhat variable as it transfers into the abutment. Also, we detailed for the minimum seat width following the seismic design criteria, and consider deflections within reason to maintain enough space around the utility that we won't have a shear failure in the utilities if we do get some differential displacement between the superstructure and the substructure. So for the inelastic section properties, and this comes from the seismic design criteria from Caltrans, we assumed 1.3 times the concrete compressive strength, and also a steel yield strength of 68 KSI. For architectural reasons, we did have a 24-inch square column with number 4 bars that can be shown there on the outside to provide some confinement to that cover in the corners. However, they were not considered to provide any seismic confinement. They weren't detailed using seismic detailing, and they weren't spaced appropriately. So while they may provide a little bit of extra resistance for that concrete to hang on, they were neglected. So for the moment curvature analysis, this is the basis for inelastic analysis. Determine the load deformation behavior of the section using the nonlinear material stress-strain relationships. Basically, that means we find the ultimate plastic moment when either the confined concrete core or the main reinforcement reaches its ultimate capacity. As we move up the curve in the elastic range, we get some cracking, get some initial yielding, some secondary yielding, and then move to the point where either the concrete core or the reinforcing steel reaches its ultimate curvature. Once we have that curvature, the basis of the pushover analysis is to take that ultimate plastic moment, determine the overstrength moments by multiplying it by a factor of 1.2 based on the seismic design criteria, and then calculate the shear relying on the dead load only, which is the surface axial force. And we know the height of the column. We have the overstrength moment at the top of the column, the overstrength moment at the bottom of the column, and divide those by the total height and get the overstrength shear. Now with a 2-foot square, 14-foot high column, the difference between the moments at the top and the bottom was fairly small. That would come into play more if we had a taller, larger diameter pier substructure. And based on the self-weight of the pier alone, the axial force may result in a higher ultimate moment from the moment curvature analysis at that different axial load and result in significantly different values there. Once we have the base shears at each column, we sum those, and then circle back and take that total summed base shear, apply it as lateral force, recalculate the axial forces in each individual column, including the dead load, but then also including a rigid overturning. And we continue to iterate that until the lateral force and the total shears converge. And this shows just that process. And I have the overstrength moments in the plastic hinge regions drawn on just one column. They would certainly be on all 4 columns. But the lateral load at the top in the first step, that lateral load would be equal to 0. And the reactions at the bottom would be equal and just the result of the surface dead load. In the second iteration, when we apply that first summed base shear as the lateral load and do a rigid overturning, we get equal and opposite reactions, certainly larger on the outside, just resulting about the center. That gives us different axial forces in each column, which will give us different ultimate moments, and then different shears. And as I said, we continue to iterate that until the lateral load and that sum of those shears are equal. This slide just shows a summary of the first and second iteration. As we can see, the shear in the first iteration, the values are equal in all 4 columns. By the second iteration, we have different values throughout the columns as we had an uplift on the exterior and an increased axial force on the opposite exterior. To further complicate the Truckee River Bridge cellular abutment, we did have the torsional eccentricity. And what that did was the rigid back wall caused bending about both column axes. So while in the transverse direction, the back wall is there and is fairly rigid and is able to absorb shear, while at the same time it causes this torsionally eccentric response and causes the bending in both directions. So the question becomes, is the change in the interaction significant in that does it allow the column to maintain more shear capacity, or does the back wall absorb the additional shear capacity because it is a rigid element? By inspection, because this element is so rigid, we can anticipate that having that back wall there will provide a better seismic response. But because the action on the column is different, it was something we needed to investigate. And this is just the column interaction diagram and with bending in both directions. On the left, we have the simple interaction diagram bending in one direction only. And with a surface axial force of 300 kips, we have a moment of about 5,700 kip feet. So then when we take that slice out of the surface on the top at 300 kips, in one direction or the other, since the column is a square, we can expect that 5,700 kip feet with 0 in the opposite direction. But as we add moment in both directions, certainly we can handle less in the primary direction. So with that, we'll move into the pushover analysis within the program. The general procedure within Midas Civil 3D is to create the elastic model in Midas Civil in the main program, then move to the general section designer, calculate the inelastic section properties, calculate the moment curvature, then move back into Midas Civil 3D and define the hinge, assign the plastic hinge to the hinging element, and perform the analysis. With the elastic model, the elements used in the elastic model need to be similar to those used in the general section designer. That seems to go without saying, but when we're iterating designs, it's possible to be in 2 programs and have a tendency to change something in one place, forget to change it in the other place. And it's just important to point out that we need to make sure they stay the same in both places, because the initial inputs in the elastic model are used to calculate the initial elastic properties when we're doing the pushover analysis. So things to verify with that are the material properties, the section properties, and if reinforcement steel is put into the original model, that needs to be the same. Alternatively, and probably a recommended procedure would be to use the linking tool to link the general section designer section to a program, and that overrides anything that may have already been put into the program and allows the elastic analysis to be based on the elastic section that was defined in the general section designer. So to get to the general section designer, it's under the Tools main menu and the general section designer. That's in a similar spot to the section property calculator, the tendon profile generator, and that'll bring up a secondary program. In that program, the first thing to do will be to define a material, and that material window Looks very similar to the material window in the main Midas Civil 3D. You can choose a concrete standard from various drop-downs and choose a concrete strength. It's also an option to simply choose no standard and input the data ourselves. And also, down in the bottom right of the material data window is the nonlinear property window. One thing to note here is, although we're defining the unconfined concrete, the model we choose for the nonlinear property of the unconfined concrete will be the default model that's used for the nonlinear properties of the confined concrete. So it's important to choose the consistent model between those two. In this case, I've chosen Mander's model. So the next step is to define the confined area, which is that confined core by the stirrups. And one thing to note here is that while I had a 24 by 24 inch square column, the way the general section designer is set up, it's easiest to define the confined core and the reinforcement steel layout by using a simple offset from the section face. And what that does is fill out the table that can be seen there. So what I did was to start, entered a 24 inch diameter column, and use the offset to define the confined core. And then once that table was written, I was able to go back and change the outside section to be the 24 inch by 24 inch square, and the confined core maintained its shape. So for the confined concrete properties, this is a window that is important to the design and has a significant amount of options. Different things can be allowed to remain dependent on other inputs, but with certain checkboxes, they can also be turned into the independent variable. For instance, the area of the confined core. That can be defined as we've defined it previously. We could also choose that checkbox and then enter a different value. This is definitely one of the tables and input windows that's best to open up the help file and read through and get a good understanding of exactly which one of those options are best for your parameters based on the design code and the specific agency that is controlling the design. Once again, we've used the Mander model for confined concrete, and we had circular spiral confinement steel. The values I use for the ultimate strains and ultimate confined concrete strength, as I mentioned previously, came from the Caltrans seismic design criteria. The next step will be to enter the nonlinear material relationship with the reinforcement steel. So I said the yield stress of the steel that's expected is 68 KSI, and that leads to an ultimate stress of 95 KSI. The other thing to point out here, there are various models to choose from in the stress-strain curve. I would recommend using a stress-strain relationship that has a bilinear relationship with strain hardening. It is possible to choose one without strain hardening, but we'll look later in the results comparison. That introduces a fair amount of error into the results. And we do know reinforcement steel to experience strain hardening, so for accuracy purposes, it's best that we include that in the model. For the steel pattern, we can enter a steel perimeter, choose a rebar material that's been defined previously, rebar diameter, and once again, this is easiest done if it's offset from the exterior edge of the section. So what I did here was again, left that exterior section as my round circular column, input the rebar shape, and then changed it back to the square column shape. So we've gone through all the windows and have all the inelastic material properties entered to our satisfaction. Run the design section to perform the column interaction diagrams and moment curvature analysis, taking into account our expected material properties and their inelastic behavior. In the results window, there are several screens. Specific to the pushover analysis, the moment curvature curve is the one we'll be wanting to look at. There's also stress contours. We can just look at the section. Also can look at the interaction curve that I had pulled up earlier with the multi-direction moment and axial interaction. But to form the hinge and export to Midas Civil 3D, we'll use the moment curvature curve. Insert an axial load to get the correct curve for our initial service, vertical reaction. Set the strain to get a reasonable range within the moment curvature graph. Too large of a strain will simply introduce data that's not relevant, and too low of a strain will have data off the graph that is necessary. We do need to turn on the display the idealized model in order to export the hinge into Midas Civil 3D. That's something to keep in mind. So we have this done. We can link everything to Midas Civil 3D using that link icon that I mentioned earlier. And we hit the link icon, it will bring up every instance of Midas Civil that's open on the machine. So if there are multiple windows open, there will be multiple windows that can be selected and either connected or disconnected from the section properties that are defined within the general section designer. Once this is created, the hinge can be exported to Midas Civil 3D. The export button, the leftmost button in the bottom right of the moment curvature curve window. Give the hinge a name, pick the interaction type, determine whether we want to manually enter axial forces or allow it to auto-calculate. Select the hinge length and also select the final curvature after failure. When we hit apply after these parameters are entered, we want to verify that the hinge is created for all required axial loads. And that can be shown down there in the message window that for negative 21 kips, the hinge was created successfully, and for 455 kips and on up, the hinge was created successfully. So knowing that my service load in each column was nearly 300 kips, I can be confident that I have hinge properties that are based on an axial load that I expect the structure to see. If that is not the case, if it turns out that we get an error message that hinge properties were unable to be created, that simply means we need to increase the final curvature after failure value to be something slightly more and allow those properties to be created. So when we hit the export button, what that does is write the hinge properties. They're behind the screens in Midas Civil 3D. It doesn't necessarily pop up and say the hinge has been created. One note on that, if you link the section to Midas Civil 3D, it does imply that a hinge has been created and give you that message. If it's not linked, the properties are there and can be found when we define the hinge, but doesn't necessarily show us just by going back to the software. So the first step of that is to define that hinge. And that's in the pushover analysis main tab. The assign hinge properties drop down and define hinge. Now we've linked the GSD to the Midas program and named the hinge. That hinge will be there, and we can click on Modify Show and take a look at those properties. If it's not been linked, if the hinge has just been exported, then we need to add a hinge, name it, and then go to the Modify Show to see the hinge parameters. Here where we pick an element type, either a beam, column, truss, or general link. I use beam elements for all my inelastic elements. Material type is reinforced concrete. I did consider the hinge length. Depending on which model, and I'll go into that in a second, I used either axial and moment in the one direction or axial and moment in two directions for the interaction type. This is a screenshot of one where I used just the one direction interaction. And then in the selection curve, we use the GSD import type. And that's where those values of the hinge that have been calculated can be brought into the program simply by clicking down and selecting GSD import type. And once again, if we've linked the program, exported the hinge, this window will be filled out already based on the parameters we entered in the export button, and it's not necessary to do these things. Once the hinge is defined, then we can assign the hinge property to the beam element, and that shows up in the left-hand screen in the tree menu. We select the hinge type to assign, select the element to which to assign it, and click Apply, and the hinge icon is shown there in the vertical column. Next step is to set up a load case and give that some name. Choose a number of steps, and in all my cases I've chosen 50. We'll take a look at that later when we're reviewing results. I've chosen to use the initial load and to just import the static analysis from the initial model run. And the increment method with displacement control, and I've chosen to select a node and stop the analysis when that node is moved in the y direction 12 inches. For load pattern, I also have a pushover analysis applied as a lateral load, and that applies as a unit load to give the shear capacity with displacements. Similarly, with the global control option, more options as far as whether to perform static analysis or import the static analysis, which static load cases to import, some convergence tolerances, and several other options where I've maintained the defaults. Once again, this is one of those windows that has an extensive help file. It's very, very helpful to go through and get an understanding of all these various inputs and how they have the effect on your design. Once everything is input properly, we can hit the Perform Analysis button. Once the analysis has been performed, the initial check is to go to the pushover curve and take a look at the base shear versus the displacement. And that's where all 50 points that I had selected earlier are showing there in red on the yellow line, all the way up to that 12-inch displacement. So certainly in this case, the column has lost all shear capacity to about 4.5 inches. Continuing the analysis up to 12 is unnecessary. I did that just for illustration purposes here. We certainly dial that back to 6 and get a little bit more refined points within the curve that has usable data. Also in the pushover analysis, there's a very similar results to the main program and a regular static or moving load analysis. We look at reactions, deformations, various stresses, forces, and the point to note here is that below the load case and combinations, there's an option to select the step, and it's possible to go through step by step and look at the forces in each element and how they change. So as this is stepped through, it's very apparent where the column is able to maintain shear force and at what step the shear force is lost as that column reaches its maximum shear capacity in the hinge zone. In my analysis, I did do 3 models. I used the first one that was just a single column with a simplified cap restraint. The reason I used the simplified cap restraint is because I wanted to maintain the double curvature. If we had not used a cap with any restraints at all, that single curvature is just a different reaction than what we would expect in a 4-column system with a cap beam. But I did do that just to maintain the single column and be able to take a look at one column at a time, and as few other interactions as possible to be able to isolate the single column. I did that. I found a maximum shear capacity at about 97 kips per column. Then I moved to the pushover analysis frame, and that was the same frame I'd used to analyze the corbel beam for the corbel beam forces for that ultimate design. Also provided the cap restraint based on the same idealized assumptions, slightly different than probably what we might expect to be the precise value from the solid top slab, but still close enough to run a pushover analysis without the interaction of everything else, and dial the analysis in and gain a sense of confidence that the shear values in the columns are what we would expect. In that case, we found about 90 kips per column of shear. Although it's possible to, or it's notable in the capacity curve that after the shear capacity was lost, there was a little bit additional residual capacity, whereas in the single column, pretty much just went to zero in the floor being bent. Because there was a little bit more force interaction and force spreading, after the force dropped off, the columns were still able to maintain slightly more shear. Once I had a sense of confidence with the single column bent and the 4-column bent models, I moved into the columns with the full abutment. And as we mentioned, that included bending in both directions. Also reached a shear of about 90 kips per column, and that was found by combining the shear in the transverse and longitudinal direction. Shear never reached 90 kips in either of those two directions, but the total shear, resultant shear, was found to be 90 kips per column similarly. There was additional shear capacity available as we expected. So as the columns lost their shear capacity, the force did spread to the back wall, and the abutment was able to continue to take force. So in the diagram on the right, the blue circle shows the first indication of some loss of shear capacity in the columns. The curve goes flat for a period of a step or two, and then begins to gain capacity again. Now, between the blue and the red, we did still gain shear capacity, or the columns were still able to increase their shear capacity. While after the red, from the red and up, all that additional force is being transferred directly to the back wall and is not being transferred to the columns whatsoever. That happened at about step 33 out of 50. This is just a slide to show that there was shear in both the transverse and the longitudinal direction with the full plate model, as we would expect with that torsional eccentricity. And here's the deflected shape with the full plate model. Zoomed in a little bit more on the two locations where the columns began to lose their shear capacity, right around that step 33. And after that happened, the back wall continued to take load. One thing to note here is that the element in the back wall is modeled as a plate, which is not able to be modeled as a plastic hinge. If we were to want to take advantage of the modeling of plastic hinges, that would need to be idealized as a set of elements. Because it's such a rigid back wall, the approximation of leaving that a plate was acceptable for this analysis. We'll look into the detailing a little bit further in a few slides, but to point out the areas of high stress concentration on the bottom and top corners of the back wall do show that we'd likely get a little bit of yielding in those sections in the event of an extremely strong earthquake. However, that dissipated fairly quickly. We expect that to lose a little bit of cover. We just want to confine that steel and make sure that the longitudinal bar stayed intact. So to compare the results a little bit, the initial moment curvature was done in Extract. And it's a very similar analysis program. The same input parameters were put in with the exception of a slight difference in the steel nonlinear model. Extract uses a simple bilinear with strain hardening model, whereas Midas GSD uses a parametric model. Just slightly different curve, slightly different response, and slightly different moment curvature output. Here we're right around 5,000 kip inches with Extract and just below 5,500 with the Midas General Section Designer. So knowing that there were some differences in the moment curvature analysis, we found a very similar relationship in the ultimate pushover between the hand model using Extract moment curvature values and the Midas Civil 3D pushover analysis using the General Section Designer moment curvature values. And the reason for that is just because of the interaction of the other elements, slight variations between those interactions. They just resulted in a response that was not quite the same as the moment curvature divided by the height. it's like I've said, the reasons for these differences, the steel model was slightly different. We had the bilinear with strain hardening versus the Kenton Park, which used the parametric strain hardening portion of the curve. As I mentioned, for comparison, if we use just a bilinear model where we go up to yield and then extend out at a flat with no increase for strain hardening, the results vary by nearly 25%. And then just some slight variations within the calculations, both in the interaction that I mentioned and then also just in rounding and any other calculation differences between the two methods. So once we had the shear values for each column based on the pushover analyses, we moved into the shear design with the element detailing. For the shear design, we followed the ASHTO LRFD guide spec, used the concrete strength, also the spiral strength for the steel strength. Once again, did not rely on any shear capacity of these outside architectural ties. That was just there to hold the concrete cover intact. And the shear value we used was the highest value from the 3 pushovers. For the columns, the detailing was based on the seismic design criteria as well as the guide spec. And that controlled things like the longitudinal embedment as well as the spiral termination in the guide spec with the extra wrap, and then also extending that tail into the core so that in the event that all the exterior concrete did fall off, the spiral doesn't unwrap and cause the concrete core to become unconfined and cause a shear failure. So for the corbel beam, I covered the design a little bit earlier. For the level of detailing, we followed the guide spec. To check the principal stresses, we approximated this as somewhat of a bent cap, although with the solid top slab, the behavior is slightly different. We did check those principal stresses to be sure that the prescriptive seismic design category D detailing wasn't required, and that's calculated on the column moments and how they transfer up into that cap. For the slab detailing, the top and bottom slab didn't require any additional detailing for seismic. We did hook the column bars as required that extended in, as well as the back wall bars that extended into the slabs. No seismic hooks in the top or bottom slab. We did, based on those stresses that we noticed in the back wall from the torsional eccentricity, include the seismic ties in the back wall, and that would just be to keep those longitudinal bars confined in the event that we did begin to spall in the top and bottom corners. That would propagate its way across the back wall just to keep everything intact in the event that that cover was lost. So to wrap things up, went through the elastic analysis into the inelastic analysis, also the MyCivil 3D pushover analysis tool, did some result checking, and went into the shear design with the element detailing. I'd like to acknowledge Midas certainly for providing the software and allowing me to do the webinar, Central Federal Lands and CH2M for the project, Design Workshop for the renderings, and the various design examples and software that we use to complete the project. It's a list of the design codes and other references that were used throughout the project. And with that, I'll open the question window and see if we have any questions.